Alright, welcome back everyone. In this video this video is essentially gonna support your study of the first chapter of Elements of Chemical Engineering by H. Scott Fogler. Okay, we're gonna talk about the general mole balances. Okay, let's get started, shall we? And there are, if you've taken a transport phenomena or a unit ops class, or if you've taken a transport phenomena class, you know there are two types of balances. You can either write a differential balance, or you can write a integral balance. All right, and if you remember stuff from your transport phenomena class, it's okay if you don't. There's no harm in that. I'm not assuming you do. Differential balances give concentration profiles. They give concentration profiles for a mass balance, for a mole balance. They give concentration profiles. For example, I have a tubular reactor and I want to know how the concentration of my reactant varies as I go from one end to the other. Okay, that's a concentration profile, intuitively speaking. All right, I want to see how my concentration, which is more concentrated here, how does its concentration decrease? Very intuitive. Okay, and in order to solve this, you need boundary conditions, because you're going to end up with a set of differential equations. So you need boundary conditions to solve spatial differential equations, because you're going to end up with diffy-Qs. Okay, wonderful. Now let's move on to the integral approach. Integral approach is not going to give you concentration profiles. It's more concerned with the output variables, the output stream variables, like what temperature is your stream leaving, like what is going to be the exit concentration, etc. Exit concentration, that's what you're concerned with. It's going to tell you what's happening at the surface. It's going to tell you what's happening at the surface of your control system / control volume. Okay, just to give you guys a refresher, a system, or in open systems, we usually use control volumes, and for the sake of this course, we're going to be focusing on control volumes. Control volumes are sometimes referred to as open systems in a Gen Chem class. Open systems in which mass can enter and leave your system boundaries. Okay, just to keep that in mind. And to give you an example of an integral balance, you have a stir tank vessel. And you have the impeller. You're dumping in reactor. You're dumping in the reactant species. You're dumping in reactants. Okay, and they're getting mixed, whooshed around. Just to give you an intuitive feel, while mixing, it's like you need to achieve a uniform profile inside the reactor, and then you have the products that are going out. And in order to analyze this using the integral approach, you're going to have to draw your control volume at the boundary. Usually it's at the boundary of the of whatever equipment you're dealing with. Sometimes it might not be, but for most cases. So now you're concerned with your inlet flow rate, you're concerned with your outlet stream, and there might be, if it's a membrane reactor, there might be a surface flux. I'm going to use capital N to represent surface flux. Okay, capital NA represents there might be any surface flux, surface molar flux. All right, just keep that in mind. For this video, we're going to focus on, our focus shall be on the integral balance. Okay, all right, so, and we're going to get to differential balances later. The integral balances, let's write that again. Integral balance is going to be applicable to a batch reactor, and the CSTRs, the continuously stirred tank reactors. I hope you guys remember the abbreviation by now. Sometimes they will be referred to as mixed flow reactors in other reaction engineering textbooks. So beware. All right, let's start off. Integral balance, let's go. You need some form of inlet. Okay, you need some form of outlet. And if I want to stick to the convention used by Fogler in his book I'm gonna write generation. Fogler doesn't write generation / consumption, he just writes generation. Okay. Alright, so the inlets are going to be in the form of streams, or in some cases you might see that they might be in the form of fluxes, like for a membrane reactor. So yeah, streams, fluxes. Alright, just figure that out. Okay, and generation, I want to point out that generation is going to be, obviously it's going to be negative for reactants, and I'm gonna leave you, since you guys love chemistry so much, at least most of you do, I'm gonna have you guys intuitively figure this out. And plus for products, and I hope that makes intuitive sense. There is like nothing, it's a very fundamental concept. Reactants are consumed and products are generated. Okay. And yeah, of course we have the accumulation term. Now let's see, let's say if we were to do this for a very vague control volume, this is how Fogler does, just to give you guys an idea. And let's say there is an inlet stream coming in, molar flow rate, FEI. Just to give you guys the notation, FEI, inlet molar flow rate of species A. Inlet molar flow rate of species A, flow rate of species A, molar flow rate. And FAO, you guys can probably guess it, since you guys are so smart, it's going to be the outlet molar flow rate, outlet molar flow rate of, guess what, species A. Alright, and let's say this entire control volume is, the volume will be symbolically represented as V, and we have a reaction happening here in which A is being consumed. Okay, we have a reaction happening in which A is being consumed, and that reaction is a function of position, like it's not uniform, non-uniform reaction. The reaction is faster at some places but slower in other regions. All right, and I hope you guys are following. So, and if it's varying with space, then how is our, if this is varying with space, if this is not uniform, how are we gonna adjust this? How are we gonna adjust this into our generation term? All right, how the hell? Well, don't worry guys, let's write the balance. In minus out plus gen equals accumulation. All right, just to have my symbols ready. FAI goes in, FAO goes out. Reaction is a negative. All right, reaction, I have A is reacting. Let's say, let me write the reaction for you. A goes to B. That's my reaction. Sorry if you guys, I hope you guys are following. This is my reaction. A goes to B. And so this is going to be, since A is a reactant, there's going to be a negative sign here. Remember, negative sign for reactants plus for products. And this is going to be an integral. You're going to integrate the RA, because RA is varying with space, with space, in order to get the total moles that have reacted. You'll have to integrate the reaction, you'll have to integrate the rate expression. Okay, and that shall equal the accumulation of A. All right, Na is just the moles of A. Na is moles of A. All right, don't get confused. Na is just moles of A in the control volume, or the tank, because the tank is going to be your control volume. Okay, and yeah, we're going to be using well mixed approach a lot. We're going to be using well mixed assumption a lot. Okay, and this will simplify our equation for almost every ideal reactor. For almost every ideal reactor, you're gonna to which you're gonna apply the integral balance. You're gonna be using this approach. Ra times V equals dNA dt, and that right here, ladies and gentlemen, is the general mole balance. All right, keep that in mind. And this is going to apply to what? General mole balance. And this is applicable to This is applicable to batch reactors, and CSTRs. All right, I'm just my OCD is kicking in, I'm sorry. But yeah, you guys will, this is not gonna apply. This is not for PFRs. Please note, this is not for PFRs and PBRs, no plug flow reactors or packed bed reactors. We're gonna treat them, they need a special treatment, they need a differential treatment. Okay, they need a differential treatment. We're gonna be doing shell balances. Okay, we're gonna be doing shell balances for these, not this integral approach. And if you guys don't worry, if you guys don't remember shell balance from transport phenomena, that's okay. That's okay. We're not gonna require a rigorous understanding of that. Just to give you guys a quick recap. 2 types of mole balances: differential, integral. Differential gives concentration profiles, needs boundary conditions. Integral, concerned with the output input. Let me just add, like, you need to give the input conditions, of course. You need to give the input streams, so that once you give the input streams, you can predict what's happening on the output streams. All right, like the exit concentration, or it could be, in this case, it's just going to be exit concentration, of course. And there might be stuff happening at your surface, like fluxes. Like I showed, there are going to be molar fluxes in a membrane reactor, for example, like I showed here. All right, an open system, control volume, used interchangeably in a lot of textbooks. And yeah, integral balance used for batch reactors, CSTRs, also known as mixed flow reactors. Inlet minus outlet. All right, and yeah, A goes to B reaction, and this right here, actually this is a general, let me make this more clear. This is the well mixed general mole balance. All right, this one right here is the well mixed general mole balance, and you guys can get which, if you want to go even more general, if you want to keep the spatial variation of reactant, then this one is like the most general, because I'm not assuming that the system is well mixed. I'm not assuming that the system is well mixed for this. All right, most general. All right, thank you guys so much, and I hope this was helpful. All right, thank you.